Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and it's always an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. It's funny how you think that this would be a sports kind of channel, because all I have is nothing but sports on the screen now, and sports jersey and stuff. Yeah, we got the Washington football team about to play the New York Giants pretty soon here, and football team's going to win this one. I'm going to go ahead and call it right now. I don't have a score for you. Let's give a score. Let's give 24 to 10. Giants aren't going to put anything up unless Saquon gets a touchdown. Football team's got Daniel Jones, man. They'll strip sack him. Gibson will get a couple touchdowns for the football team. I don't know. We'll get some here and there. We'll see how my prediction works out. Anyway, guys, let's do some stuff today. Last time you saw me do some things with transforming polynomial functions. I also talked about even and odd functions, but it was really just a bit of a teaser. Let's dive into it a little bit more. I'll show you graphically, once again, how to determine whether a function's even or odd or neither. And we'll also do it algebraically. The heavy stuff I think will be algebraic, but we're going to start with the graphical stuff. And I prepped just for the first few algebraic ones, I'm going to show you what those graphs look like also to confirm that they are indeed even, odd, or neither when we do them. So I have a sheet here, and we can play with it. Hang on, let's get the right one. Okay, I have a sheet here, and let's go ahead and play with it here. And the first 6 problems are these graphs where we are going to determine whether they are, using possible symmetry, whether they are even, odd, or neither. Now, a function is even graphically if there is symmetry across the y-axis, which means if I reflected this graph, I would get the same graph out as I currently have now. Now, I do have tools in order to be able to reflect these right now, so I'm going to go ahead and do that. If I flip this graph over, do I get the same appearance of this graph right now that I see? Let's check it out. Nope, different graph. This graph goes down and right, while this graph goes up and right, or down and left, or whichever way you want to put it. These are different graphs. They are not symmetrical. This is not the same graph both ways. So no, this is not an even function. If it were an odd function, what we would look to see is if it has what's called point symmetry at the origin. If I could rotate this 180 degrees and still get the same graph out that I have right here. Let's see. I turn it around. You might say, oh, yeah, look, it goes up and right. But it's not the same location. You need it to be the same graph. The same x, y values come out after a rotation of 180 degrees. Now, how can you do this? I guess you could rotate your paper, reflection, look into a mirror. I'm kidding, of course. What I mean is you just got to see the symmetry for what it is and be able to tell. There are other ways. We'll talk about it here in just a moment. It just has to do with the idea of what y values you expect for your x values and your negative x values. But this doesn't seem to have any sort of symmetry across the y-axis or the origin here. Because once again, let me do the rotation again. Look at the rotation versus the original guy right here. Rotation, original guy, not the same graph, different intercepts. And obviously, look, the numbers flipped over. That's the nature of me turning the graph around. But that is not the same graph right there. It is not symmetrical across either. This is neither. Let's look at number 2, though. Look, let's reflect it across the y-axis. I'm going to flip this over. You'll be able to tell when the numbers flip over. Flip left, right, boom. You see them flip over? But look, we have the same graph on both of these. I flip left, right, boom, 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 boom. I have the same graph. And make no mistake, maybe I didn't make it perfect as far as whatever goes, but it's the V shape. It has the vertex at 0, 1, and it has the right, it still goes upward, all that kind of stuff. This is the same graph. This is what's known as an even function, reflection across the y-axis. This is even. The other version of even that we're going to do a little more in the algebraic portion of this is for whatever x, y value I choose on this graph, for whatever one I choose on the graph, the negative x value, the negative x equivalent has to have the same y value. So if I choose like 6, 7 right here, you see that 6, 7? That means there better be a point on here that's negative 6, 7, and there is. There's negative 6, 7. And it's not just coincidence, it's that one. It'll happen for every x value and its opposite, that they'll share the same y. That's what gives you the symmetry across this line. Everything reflects across it right there. And that's what it is that we're doing, and that's what we see. So yes, this is an even function. That once again, for even functions, I'll write it later, but the opposite x value shares the same y value as its positive, negative counterpart, whatever it is. All right, number 3, same thing. I'm going to test for even first. And if you can tell, maybe you can make a prediction. Yes, this is indeed an even function. Watch me flip this thing over here across the y-axis. And when I say across the y-axis, guys, I just drew the line. The y-axis is the mirror. So flipping across it means going this way, left, right, left, right. So there's that perpendicularity going across that thing. And, you don't go up, down. That's reflecting across the x-axis. That would be flipping it over, say, whoops, I went the wrong way. That'd be going over, say, that way like that. That's not what we're doing. So flipping across the y-axis there, yes, it does it. This is also an even function for that reason. It shares the same y value, whether you take a normal or opposite x value. Those are some even functions there. All right, let's take a look at this one here. If I flip this one over, what's going to happen? Well, you get a different looking graph right there. It's going to go this way, down and right instead of up and left. So this is not indicative of an even function here. Is it an odd function? Well, let's check this thing out. Let's rotate it 180 degrees. Let's see what we're going to get. Hey, look at that. I'm going to undo and redo. Let's look at these graphs here. See that? This is an undo redo of the rotation 180 degrees. And don't let the numbers fool you there. This is, the axis is still there. This is the same graph through rotation. This is an odd function. This is what odd functions do. And I see this thing glitching. Let me pause my screen for 1 second here. Okay, sorry, I'm back. When my pen thing is no longer a pen and it goes away, I don't know what causes it, but it's hard for me to write and do these. Anyway, so this is an odd function here. And what happens specifically with an odd function, besides the rotation? Well, actually, here, let's talk about the rotation. So observe a point on this graph that would be like, say, I don't know if this is like 2, 2, but pretend like it is. So 2, 2. What happens, though, when I rotate this thing 180 degrees? Where does that point go? It turns into like the -2, -2. What happens is the x changes into its negative version and the y changes into its negative version. So what we're really looking for, let me do a better one. Let me choose one with different numbers. 3, 8, I think. 3, 8. If you have 3, 8 on your graph, for an odd function, you need -3, -8 on your graph. That when you switch the x sign, the y sign also switches. And that's what happens here. Which does then require that you have the origin as one of your points. For an odd function, it has to cross through the origin. Otherwise, if you have some different y value at that x, a different y-intercept, then the negative version of 0, which is 0, would have the opposite y value. And you can't have different ones there, right? They need to be in the same spot through rotation, and you can't have that. So they have to go through the origin to be an odd function. So automatically, this was never going to be an odd function. This was never going to be an odd function. This was never going to be an odd function. That doesn't mean that all things that go through the origin are odd, but you can't be odd if you don't go through the origin. Okay, number 5 here. Again, a reflection for even, test of even, no. Reflecting across is a different graph. I rotate 180 degrees. Okay, look, this one seems to pan out. So look at this one. Same line when I rotate back and forth. 180 and back. That's an odd function. And one more time, just looking at a test there, it does go through the origin. And for any xy value, such as 1, I guess 6, there is a -1, -6 also that it goes through. And that's, those are testing by example, but at some point you got to give and say that yes it is. And I'm not trying to trick you whether or not it's odd. Now this one may have tricked you a little bit because it goes up and right through that rotation, but remember this does not go through the origin. It goes through a different y-intercept when I rotate it versus not. And look, going back to that xy stuff, right? There's like 2, 5 as a point here, but then there's -2, like -10. Those are not the same or opposite y values for those opposite x's. And number 6, I flip. Oh wait, let me write that. That's odd. And number 6 here, we've got a left-right flip right here. Is it symmetrical across the y-axis? Heck no. When I rotate it 180 degrees here, also, heck no, not the same graph. This is a neither. It also doesn't go through the origin. So this is a neither here. So it looks like 2 evens, 2 odds, 2 neithers, and we are set for the graphic ones. All right, so that's how you do it graphically. Let's now verify them algebraically and see what's going on. And I will confirm the graph versions of these after I test them algebraically and kind of show you what I'm getting at. So to do something that's even here, to get an even function that's even, what you need is for, remember that f of x means y, right? F of x means the value of y at that x value. So what we need is the value of y for any function that you have to be the same when you plug in either some x value or its opposite. When you plug in some x value or its opposite, they need to share the same y value. They need to be equal. This means the y value when I plug in the opposite of x. This means the y value when I plug in x. They need to share the same y. If they do, your function's even. If your function's odd, what happens is when you plug in your negative version of some x value, that needs to give you the opposite of the y value that you had when you plugged in your normal x value. you need to get the opposite sign. So even functions get the same y value when you plug in the opposite x. Odd functions get the opposite y when you plug in the opposite x. Neither is an instance where that doesn't happen. And remember, it could happen just even once, but you need it to happen all the time. That's why I say x right there. Is this my cold water? Yeah. That's why I say x right there. I need to do it for every x, not just one x. This is for all x's in your domain. So let's look at number 1 here. F of x equals x cubed minus 6x. What I'm going to do is I'm going to give undeniable proof whether or not this is even or odd or neither by substituting in negative x for x. If it helps, I'll do a real number first so you understand the idea of substitution. Let's go ahead and let's try say f of 4. Let's substitute some number into here and make sure you understand the idea of input. 4 is taking x's place. That means wherever you see an x in the equation, I'm going to place a 4. And I'll wrap it around parentheses. 4 cubed minus 6 times 4, for example. 4 cubed is 64. 6 times 4 is 24. 64 minus 24 is 40. So what this is telling you is there's a point on the graph that is 4, 40. When x is 4, y is 40. Awesome. What about the negative version of 4, though? What if you plug in negative 4 for x? What we'd expect for an even function is to also get 40. What we'd expect for an odd function is to get negative 40. And what we'd expect for a neither function is probably for it to not be 40 or negative 40, expecting it to be something different, unless we landed on some sort of false positive. That's why we have to try x's instead. But if I substitute negative 4 into here, notice what happens here. We are going to cube negative 4 and we get negative 64. Then we are going to be subtracting 6 times negative 4. Negative 6 times negative 4 is positive 24. So we have negative 64 plus 24. That becomes a negative 40. That means there's a point on our graph that's negative 4, negative 40. And unless it just happened to be coincidence, what it appears to be is that when I plugged in some x value and got this y value, plugging in the opposite x value got me the opposite y value, which is indicative of an odd function. Does this guarantee that it's odd? No, it could be coincidence. Let's check it out for real this time. If some x here gives me this y value, and remember, this represents a y, right? Because this is y equals this. If it gets me this y value right here, let's see what happens when I plug in the opposite x. And what we're expecting, since this clearly isn't even, what I'm expecting is if this is odd, is that I get the opposite of what I got here. Sign-wise, I get the opposite. So let's substitute negative x for x everywhere that we see an x. So negative x quantity cubed, again, 3 negatives multiplied together leads you with a negative. So this is the equivalent to having the opposite of x cubed. Negative 6 times negative x is positive 6x, and this is what f of negative x equals. Now you can look at this one of two ways, and I'm definitely going to have to look at both. So here's one instance, writing it like this, and what you can do is you compare. You compare f of x to f of negative x, and you look at each term, and we say, all right, I have x cubed here and negative x cubed there, clearly opposites. I have negative 6x here and positive 6x here, clearly opposites. It looks like every sign changed, which is indicative of y being an exact opposite of what that is. This seems to verify that this is indeed an odd function. If you need a second look at it, I don't know how good you are at factoring, but hey, if I factor a negative 1 out of this thing, I could also write it like this. F of negative x equals the opposite of x cubed minus 6x. So if I factor a negative out of here, the x cubed turns positive, 6x turns negative. Now if you compare these two here, what's the difference? Well, here you have the positive version of x squared plus minus 6x, and here you have the negative version of x cubed. If I said squared, I'm sorry. Negative version of x cubed minus 6x. This is an exact opposite y value of this y value here. And you know, that's going to be an important talk for later, this especially, because we're going to deal with products that we can't distribute into and get different terms. We have to understand the idea of quantifying something, of quantities. Once I wrap this around parentheses like this, I have quantified it, and you treat this almost as a single number, almost as if this was just a big-ass y, right? You can just treat this as a y, like here's a big y and here's a big y right here, only this is the negative y. It doesn't matter that there are multiple terms in there. Once it's grouped, it is quantified. And if I have the exact opposite thing quantified here compared to here, then I have the opposite sign. And I know I'm spending a long time on this problem, but that is indicative of an odd function. You want to see either version, either this. This is fine, but not all of them can appear like this because you can't always keep them as separate terms. But this is definitely an odd function. Now, if you want to see kind of a little more proof of it, let's go to, I have a graphing calculator thing here. So let's go to this on this problem. And here's the x cubed minus 6x graph in and of itself. And they're fun to look at sometimes. They got all the squigglies right here. Let me give you what this would look like if this was an even function. So here's f of x being x cubed minus 6x. What if I did f of negative x? What's going to happen here is you are going to get this blue guy right here. Clearly, this isn't an even function. If it was an even function, these two graphs would be the same. One would be right on top of the other. F of negative x being the same y as f of x, this is not true. But what we are actually testing, I can actually ignore f of x right now. What I want to see is if f of negative x is the same as negative f of x. That if I flip this thing over the y-axis, like here, is that the same thing as flipping this thing over the x-axis, like here? And the answer is yes. Look how the green and the blue are perfectly on top of each other because flipping this over the y-axis is the same as flipping over the x-axis right there. This is how odd functions work, that they match up with that kind of reflection, that the negative x's inherit the negative y's of the original function. By negative y's, I mean when you change the sign of these things. Anyway, I'm spending a long time on this problem, guys, but these are the nuts and bolts to get you into the rest of them and start to make sense of it. Obviously, when I get different kinds of things, it'll change. But, that's how I roll, right? All right, let's go to number 2. G of x equals x to the fourth minus 2x squared. So let's test g of negative x here, and let's substitute negative x into this guy. And by the way, I just wanted to mention, this is something that you can't prove by example. I can't plug in 4 and negative 4 and say, hey, therefore all of them are true. This very much could have been a false positive. Now, it wasn't. This was an odd function, and you can support your answer by testing things or make more sense of what's going on by testing them that way. But you got to prove it by using the negative x stuff. The only thing I can think of is you can disprove even and odd by saying it's neither, by using a counterexample and saying if I don't get the exact same y, or if I don't get exact opposite signs, then it's neither even nor odd. And when we find our first neither, I'll do that. Anyway, let's substitute negative x into x right here. So negative x raised to the fourth power minus 2 times negative x quantity squared here. So what happens here, the opposite of x to the fourth, to us might as well be x to the fourth, because you have a negative times a negative times a negative times a negative. 4 negatives multiplied together results in a positive. So these are the equivalent. We're simplifying what we substituted. And then we have negative 2 times negative x squared. Now be careful with one thing here, guys. I can't do negative 2 times negative x to start with because multiplication does not occur before exponentiation. I must do this negative x squared first. So let's keep the negative 2 as it is, and let's do the opposite of x squared, which is, negative x quantity squared, which is x squared. So negative 2 times x squared goes here. And that's what we get. That's what g of negative x is. So now as we look at this, the question is, how do these two things compare, the original g of x and g of negative x? And the result appears to be, if I quote my cousin Vinny, not literally the character Vinny, but from my cousin Vinny, identical. X to the fourth minus 2x squared, x to the fourth minus 2x squared. Whether I plug in a positive x or the opposite, an x or the opposite of that x, I seem to be getting an equivalent y value. Same sign, same value. X to the fourth minus 2x squared appears in both. To confirm it, we could substitute a value. I could try something like f of 4 again right here. G of 4. Let's try g of 4. Let's do 4 to the fourth power minus 2. This isn't confirming it. This is just, it's feeling better about it. Feeling more confident. 4 to the fourth power, oh gosh. Oh, I picked big numbers at 256. So let's see, 256 minus 4 squared is 16 is 32. 224. So 224. So there's a point on the graph that's 4, 224. Let's check out g of negative 4. That's negative 4 to the fourth power minus 2 times negative fourth quantity squared. Look, it's going to be the same thing. Negative 4 to the fourth is positive 256, like this. Negative 4 squared is positive 216, like this. And times 2 is 32. 256 minus 32 is also 224. So we're getting the same value out. We're getting the same value out with that one. It would happen for any x and opposite sign that you plug in. That is indicative of what an even function would do. Even functions do that. This function is even. And I'll show you what this one looks like on a graph as well. I have that kind of pre-prepped for you. And what we're expecting here is the same y value out over here. Here's my g of x, that little w shape. That's the x to the fourth minus 2x squared. If I put in g of negative x, I should get the same y values out as I do here. In other words, there should be perfect overlap. When I click this button and put this in, see that black? That's going right over the purple because these are the exact same graph. Doesn't matter that I'm plugging in the negative x values. We're flipping it over to the y-axis, and it's the same thing back out, and that's what we get. That's confirmation. All right. Not that you're supposed to be graphing these. They want you to solve it out algebraically. Number 3, h of x equals x squared plus 2x plus 1. Let's attempt h of negative x and see what goes on here. And by the way, I have 7 more problems after this. I hope you know that. I'm flipping over this page after that. If you get it after this, great. There are other kinds of problems that occur that aren't just polynomials. The opposite of x squared plus 2 times negative x plus 1. So the opposite of negative x quantity squared is positive x squared, as we've established. Now, 2 times negative x is a minus 2x right there. And then we have a plus 1, which seems to be unaffected as a constant. Okay, so here's the simplified result right here. And what we do is we kind of compare the two and we say, are they the same? They're close to the same. X squared and 1 are the same, but we have a 2x and a negative 2x, and that sign changes. And I don't think it's enough to also call this an odd function either. What you would need is all signs to change for this thing to clearly be shown as an odd function, as in a negative x squared and a negative 1. Now, I got to spoil something for you a little bit here, guys. This 1 is always going to stay a 1. That was never going to change into a negative 1. There was no way this ever could have been an odd function. When we look at the graph, you're going to see it doesn't cross through the origin. It has a y-intercept of 1. Sorry, this has a y-intercept of 1. If it doesn't cross through the origin, it's not an odd function. Now, is it an even function? Unfortunately not. There's a plus 2x here and a minus 2x here. They'd have to be identical to be even. This is a case of neither. It's not exact opposite. It's not exact same. It is a neither case. Now, I could try and substitute something into here. Let's see what we're going to get. We expect not the same y value, not the opposite y value. We expect two different y values. How close or how far, it doesn't matter. If they're different, they are not the same, and that's in either case. So let's try h of, I've been using 4s. Let's keep at it. H of 4 here, that would be 4 squared plus 2 times 4 plus 1. 16 plus 8 is 24, plus 1 is 25. When x is 4, y is 25. When x is negative 4 here, you get negative 4 quantity squared plus 2 times negative 4 plus 1. Negative 4 squared is still 16, but then 2 times negative 4 is minus 8. So 16 minus 8 is 8, plus 1 is 9. So 2 different y values, not the same, not opposite. This is a neither case. This is neither even nor odd, by definition, what they do. Now let's look at that graph. This is the last graph I will look at because all the other ones we're just going to trust the idea of them. Here's the original right here. Now, let's test an even function against it. An even function would say, just like with this one right here, right? If I plug in negative x, I get the same y's out, so I get the same exact graph and overlap. So let's test for even. You can probably tell it doesn't reflect over properly, right? When it reflects over, this is what you get, a different graph. A different graph. The other test is for odd functions. Does the negative version of x give us the negative version of y? No. No, it does not. These are different graphs as well. So not an even, not an odd, neither nor. We move forward. And move forward we shall. Let's start looking at the last 7 problems. Number 4, x squared plus 6. This time I'm not going to do any more graphs, just the algebra. I'm not going to test other numbers outside of it unless I feel it's absolutely necessary to teach a new element of what we're doing. The opposite of x squared is x squared, so we get x squared plus 6 out. F of negative x, to tie this in, guys, one more time, f of negative x seems to give us the same things as f of x in this case because these are identical. These are identical. This is indicative of an even function, symmetrical across the y-axis there, and that's what that is. And I'm going to move forward. Number 5, 7x cubed minus x. That's for g of x. G of negative x is going to give us 7 times the opposite of x cubed minus the opposite of x, like that. So negative x quantity cubed is negative x cubed times 7 is negative 7x cubed. Opposite of negative x is plus x, like that. All right, so that's our result there. Now, if you compare the two, 7x cubed, negative 7x cubed, opposite, negative x, x, opposite terms in a simplified format. Also means you could factor out a negative 1 and you get the opposite of negative 7, the opposite of 7x cubed minus x. The exact opposite of this quantity here means that this is an odd function for whatever I'm getting, not f, For whatever I'm getting here for g of negative x, it becomes the opposite of your g of x, that the negative x's give you negative y's. Negative x's give you negative y's. That is what an odd function will indeed do. H of x, let's check it out. Let's use green. H of negative x would give us the opposite of x to the fifth plus 1. Okay, the negative x quantity to the fifth is negative x to the fifth power, and then plus 1 right there. So that's h of negative x. So, okay, that sign changed, but the 1 was a 1. It remains a 1. It's a constant. Never could have been an odd function because the y-intercept not being at 0. 0, 0 at the origin, and these signs change, so it's not identical. This is not even, this is not odd, this is neither. Now before I move on to the last 4, because I think we're going to get different kinds of functions here, I see a radical function, an absolute value, and well, that one's a polynomial. That one's good. Going back to the first 6 of them, I don't know if you noticed this or if you know anything about what's happening here. Now, this is a case of not being biconditional, which means just because it works one direction, this doesn't work the other direction. My point of this is, let's pretend for a moment all fire trucks were red. All fire trucks are red, but not all red vehicles are fire trucks. All polynomial functions with even degree terms, like this is degree 2 and this is degree 0, if you know anything about constants, with even degree terms, all of those are even functions. This is an x squared. If you saw an x to the 4th, x to the 6th, this is technically x to the 0. 0 is an even number. All those things, if those are the only terms that exist inside there, even degree terms, you actually do have an even function. Let's look and see if we can find the other one that was an even degree function. This one, x to the 4th minus 2x squared. That at 4 and 2 right there with those degrees, that is an even degree. That is going to be an even function as well because they have all even degrees going down in the polynomial. Odd functions, all polynomials with odd degrees, this is degree 3, this is degree 1, only exclusively odd degrees will actually also indeed be odd functions. Not all even functions are just polynomials with even degrees. You can have other kinds of things, and we're about to run into possibly some, and same with the odds, but that is true. So I knew automatically right here, this is degree 2, degree 1, and degree 0. I actually knew that because there was a mix of even and odd degrees, this actually would be a neither case. It's just not symmetrical across the y-axis or the origin to be so. And same with this one right here. This is degree 3, this is degree 1, that works as an odd. This is degree 5 and degree 0. It's a mix and match of even and odd here, or odd and even, and that one's a neither case. So there are ways that you can determine within polynomials whether they are or not. That doesn't mean that all even functions, because these ones aren't polynomials right here. So now you got to do extra work to figure it out. But a nice little tidbit there. I don't think I told my students that yet. I think it was over the top. They might not really know what degrees are because we haven't spoken of them. But for those who want to know, that's a nice little trick. This one, honestly, off the top of my head, I wouldn't know. I'd have to know more about this thing to tell you. So number 7, let's go ahead. Let's play with it. Let's try f of negative x here. So we're going to take the opposite of this x right here. We got negative x times the square root of 4 minus quantity x squared there. Now, negative x squared. When I do negative x right here, that is just a negative x. Okay, great. And this 4, remember, you don't do minus the negative here. We got to do negative x quantity squared first, and that gets us x squared, and we're going to subtract the x squared. Now, this is one of the tricky ones here as far as you understanding. This is where I wanted to talk. This is where I want to get in the quantity talk here. Because as we look at these, you can tell that they're not identical. This inside part is, but the outside's not. This is an x, this is a negative x. But then you'd say, well, let's see, this sign, if we wanted an odd function, we'd need a negative 4 here and a positive x squared here. Because what you said was they all need to be different signs for it to work. No, what I said is the y's need to be opposite signs. And what you're doing when you're looking at y's is, in a polynomial sense like this, you can just do term by term. Like this one here. This was term by term. I got a negative 7x cubed instead of 7x cubed and a positive x instead of a negative x. Term by term, they were opposite signs. That's great. But this is not term by term. This is a product. This is negative x times this quantity. By and large, guys, the square roots are grouping. Guess what? This whole thing's a grouping right here. I could put the negative in there as well, but my point is I want to compare it to this grouping here. This is a grouping because it's a product of something that I can't distribute into. And I can't break, I can't penetrate in any sort of way. It's a square root. I can't take the square root of it. This doesn't turn into 2 minus x. No, that's not how that works. It's different in its own right, and we must quantify this thing. We must understand. That's why I was so gung-ho about talking about quantifying these things and saying if I have the opposite of this quantity, then I do have an odd function, and that's what this is. Here's a positive version of x times the square root of 4 minus x squared quantified, and this is the negative version of x times the square root of 4 minus x squared quantified. Remember, this negative has everything to do with this square root of 4 minus x squared, just like it has to do with the x. Not that I distribute it, it's a single quantity. And I know I'm getting very passionate about this because it's something that I really want to make sure that I live up. That's what I'm doing in terms of quantifying. I don't have to put the parentheses. I'm just giving you the idea that I'm not changing signs in here. These aren't separate terms from this x. It's multiplied in a grouping. They're not separate terms. These are all part of the same thing. So all being a part of the same quantity and being the exact opposite of this quantity here does indeed mean it's an odd function. And I'd love to graph this one for you guys, or I'd love for you to go into Desmos and check it out. But what you would check and see is, does the opposite thing here, the opposite x, give you an opposite y? Do f of negative x, write out f of x, do f of negative x, do negative f of x, see if you get the exact same graph out. And you would. All right, number 8. Let's do the same thing here. We're g of negative x here, and this is opposite of x to the 4th. And remember, what you can do, by the way, try and plug in some real number. Well, there aren't many good numbers you can plug in because got to take the square root of a positive. Oh, well, anyway. The negative x to the 4th there times 1 plus negative x. When I simplify this, negative x to the 4th power is a positive x to the 4th, and then times the square root of, that turns into 1 minus x, right? Square root of 1 minus x there. So although these are the same here, you have an inside quantity, the square root of, let me rewrite it. Square root of 1 minus x, which is different, right? That x changes sign, therefore these are different quantities right here. And them being different quantities automatically kind of nullifies it, right? These are different. These are different numbers entirely. It's not just changing a sign. This is a neither case. It's not identical. It's not opposite of. This is a neither case. And I was so glum that I wrote it in lowercase instead of all caps there. All right, number 9. There's a lot I could say about number 9, starting with if you know how to graph this, then you would know what this is. Absolute value graphs are V-shaped. With the -1, it means you translate 1 unit down there, and it's a V-shape. It is symmetrical across the y-axis. Make no bones about it, guys. This is an even function, even though it's not of even degree and stuff like that. It will be even. But let's get into the nitty-gritty of what happens with the absolute value stuff here. Now, one thing you can't do, you can't say that the absolute value of negative x is x, because you're forgetting your place as far as x could potentially be a negative number. You're forgetting, like, look, what if x was -2? What if x was -2? What's the absolute value of the opposite of -2? Is it -2? Nope. The opposite of -2 is 2. The absolute value of 2 is definitely not -2. That doesn't work. So you can't ignore the fact that x could have been a negative number. Now, I did not ignore the fact that x could have been a negative number here. The point is, when you raise that negative number to the 4th power, it still becomes positive. Here, when you take the absolute value of something, you don't want it to turn into just a single x that has no effect. So it's got to stay inside absolute values. That's going to be the first bit. So when I'm plugging this thing in here, and I get the absolute value of negative x here, x has to stay inside the absolute value. But what about the negative? What about the negative? Let's dive into a property, guys. Let's dive into a property. And the property is absolute value of a product. Absolute value of a product. Did you know that you could take this and split it into the product of two absolute values? I don't know if you knew that. And you might say, Mr. Robinson, we don't have a product right here. Oh, yes, you do. This is -1x, which means it's -1 times x. So this is absolute value of -1 times the absolute value of x. We can split that up, right? That's -1 times x. And there's a -1. Now, the absolute value of -1 is 1. It is 1, right? And 1 times anything is just that thing. So I'm going to kind of let this thing go away. Like, bye-bye, you're gone. And you know what this now says? H of -x equals just the absolute value of x minus 1. That's the end result of this. And what do we have? Identical. When you plug in a -x and get the same y, you have what is known as an even function. an even function right there. And you saw the graph that I really roughly sketched, and there it is. All right, last one, number 10. If you heard anything about what I said about polynomials earlier, this is degree 6 polynomial. This is a degree 2 polynomial term. That does mean all even degrees in this thing. Guess what? This will be an even function. This will be an even function. Let's go ahead and try and plug it in and see what happens. G of negative x here equals different color. This game's about to kick off pretty soon. We got Joe Buck and Troy Aikman calling this game. I forgot they did Thursday Night Football now. 1/4 times negative x to the 6th power minus 5 times negative x squared there. Let's see it. 1/4. Hey, this is why they always work, because you raise to an even power, this becomes a positive result. So this becomes x to the 6th. Minus 5 times, remember, do this part first, negative x quantity squared is x squared. And guess what? You got the same thing out, identical to this one right here. Because they're identical, this is an even function. This is once again why all the even degree terms together in a polynomial make an even function, and why the odd degree terms together in a polynomial would make an odd function. Remember, constants count as even degree. If I had a +4, it would still work. As the 4 wouldn't change, it would still be a +4. Anyway, that's an even degree one there, and that is it. So that'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching this one. I sure hope it made sense, and all the explanations that I had were a large part of helping you make sense of this. Thank you so much, guys. I'll see you in the next one. Take care.